What's going on, my children? Welcome to MCAT Mondays, Gen Chem episode 2. This is all one take, by the way, so that's why it's pretty hard. Okay, where we left off was absorption of energy, emission of energy. Okay, absorption means absorbing energy, obviously, which means delta E is greater than 0. That is absorbing energy. And what that means is, like in a visual way, if you have a colorful background and an atom or electron that absorbs the energy, what that would be was like a black line on this colorful background showing that it's absorbing that specific wavelength of light. Now, the complete opposite is emission, which means the electron is releasing energy, giving off energy, and that's denoted by delta E is less than 0. And the visual image of that would be like a dark background, and the specific electron would be giving off a wavelength of light, showing a little bit of color in that dark background. And here's an example of like experimental setup of absorption of energy. So you got like an ionization energy right here, which is like a form of radiation. And you got like a gas, an elemental gas. This ionization comes in, hits one of those gas particles. The electron gets absorbing energy, and it releases off. This ionization comes in, hits this prism, and gives you a spectrum of light. Whichever wavelengths of light are absorbed would be in dark background. Does that make sense, cameraman Sam? Bet. Okay. Now again, we got this equation. Energy is equal to Planck's constant times C over lambda. This quantity right here is also equal to frequency. And I'll just give you like the list of electromagnetic spectrum with the highest in frequency, in order of frequency. Gamma rays is the highest, X-rays second, UV, visible, IR, which is infrared, microwaves, and radio waves, increasing frequency. And that obviously also means increasing wavelength in this direction, based off of that equation that I just said, C over lambda is equals F, showing a reciprocal relationship right here. Now I'm going to give you guys a little bit of a practice problem, okay? You got to find lambda, and you're given, let's just say, an electron releases energy from n equals 4 subshell level, or energy level, to n equals 2. It emits a photon through this, and this photon has an energy level of 2.55 electron volts. Okay, now you have this equation, right? E is equal to HF. You can manipulate that to E over H is equal to F. Okay, now you have the E and you have the H, which can make you this. F is equal to 2.55 electron volts over 4.136 times 10 to the minus 16 electron volts, which you said last time. That's the Planck's constant in electron volts, and that should give you the answer of 6.17 times 10 to the 14 hertz. And hertz is also in 1 over seconds as well. Remember these units because on the exam, you could cross out multiple choice answers based off of what the units say. So like it just makes it easier. Whatever makes it easier, just try to do that. So you got that as the frequency, right? And lambda is equal to c over frequency, right? We said that, right? So basically it's 3 times 10 to the 8th over whatever we got, which was 6.17 times 10 to the 14 1 over seconds, and that is around 5 times 10 to the minus 7 meters, or 500 nanometers. Okay. You got this quantum model as well. So we're going to go into a different topic, right? This is going to be the quantum model of the atom. And there are 4 quantum numbers, okay? One is the energy level, which is N, and is energy level. And the variation of numbers from this is from 1 to infinity. And you can tell N by the periodic table. I'll just say, looks like something like this. It's a little bit bigger. This is your N, basically, where 1 is the top of the periodic table. Second one is the P, or no, second one is the L, okay, which means subshell of the specific atom, and that's in this periodic table. What that means is, okay, so this would be your S, P, D, and F blocks, and L is your subshell. S would be a subshell, D would be a subshell, P would be a subshell, F would be a subshell. And what that is numerically would be whatever 0 to n minus 1, that would be your L. So like again, if you go down to n, the energy levels, you just subtract 1. That shows you how many L's are in that. And L is from, again, I showed you that the blocks, right? L would be more like this, like increasing L's like that. So since the first level has, in the periodic table, has only 1 as the n, there will be only one L number, which would be 0, and that's denoted as S, okay? And for the second one, you have 2 energy levels, okay? Now what that means is you got 0 to 1 as the L's, L and the number of L's in there, which is the subshells, which means that you got a subshell of S subshell, which is 0, and a P subshell, which is 1, and then so on, each increasing n gives you more and more L's. Well, did that make sense, Cameraman Sam? Yeah? Okay. And number of electrons again is S has 2 electrons, P has 6 electrons, D has 10 electrons in that subshell, F has 14 electrons. Okay? Now, the third quantum number is denoted by M underscore L. Now that is the specific orbital orientation in a plane of space. And numerically, it is whatever minus L is to L. Okay? Now I'm going to draw some images and show you exactly what I mean. So now you got L, let's just say L equals 0 for the S subshell, which we said before. Now since it only has one number, or one L number, you only have one M underscore L, which is 0. So there's only one orientation for the S subshell, which is a sphere. Now let's just say you have a P subshell. ML is equal to, or L is equal to 1. Now all of a sudden you have 3 numbers, -1, 0, 1 for M underscore L. Now this denotes the specific orientation of that orbital. And a P, and this specifically is the P orbital, okay? Which looks like a dumbbell, okay? Now there's 3 orientations in the XYZ space. Let's just say this is the Y orientation, this is the Z one, and this is the X. That makes sense, cameraman Sam? Okay, bet. I'll just give you the specific quantity of MLs. So one would have, the S1 would have only 1 orientation, P would have 3 orientations, D would have 5 orientations, and F would have 7. Okay? Now the last quantum number is electron spin. I know I'm going over 10 minutes, hopefully you guys can keep up. Okay, electron spin. And now there's only 2 forms of this, and it has nothing to do with the other quantum numbers. Okay, there's only 2. There's an up spin and down spin, and this is denoted by +½ -½ Okay? Now this is important specifically for the concepts of paramagnetism and diamagnetism. Okay? Paramagnetism means some of the electrons in the atom, some electrons in the atom are unpaired. They're loners, okay? They're very lonely. They have no friends, okay? So you're gonna end up like with this. Let's just say this is in a P subshell, right? That's the spin numbers, okay? In each subshell, there's going to be 2 electrons in each subshell of the P, and we have 3, right? Remember, 1, 0, -1. So you got 3 of those in this P orbital. And now in this paramagnetism, you only have 1 electron. Could be an upspin, could be a downspin. There's only 1, okay? It's lonely. It's unpaired. Now what that makes the specific atom do is it makes it more likely to align with an electromagnetic field. Okay? That makes sense, cameraman Sam? Now there's another one, okay? Because there's obviously going to be completely filled electrons, or electron shells, or subshells. Now that term is called diamagnetism. Okay? Which means all electrons are paired. Now this one is actually repelled by an electromagnetic field. Because again, they don't want to, they're not attracted, there's no charge anymore, right? They're all paired. Repelled by electromagnetic field. So an example in the periodic table, helium would be diamagnetism, and then carbon would be paramagnetism. Okay? I think that's all we have time for. Hopefully you guys understood. If you guys need me to explain anything, let me know.